looking for the cases where you can have reuse, or where the arithmetic cost is a large multiple of the data set size.
So what's a good ratio of byte flops? 1 to 4?
Oh, no. You would want probably 40 flops per byte to make it worth your time, at least, maybe more. Because the time it takes you to get the data there from the host in the first place. So to give you an example, so Barry, who's maybe over there, Barry has been working on a really interesting analysis tool for VMD called Timeline. And what it does is it basically performs a bunch of standard molecular dynamics analyses on every frame of a trajectory. Now, a lot of these turn out to be very, if you look at them in isolation, each one is a very trivial number of floating point operations relative to the size of the data. So if I just wrote one CUDA kernel to, for example, calculate the RMSD between two structures or something like that, that's barely enough floating point to be worth even bothering sending it to the GPU. But, and so this is interesting. So I was looking, he gave me a list of all the things he'd like to see run 100 times faster. And so I look at the list and I say, wow, none of these have any significant floating point by themselves. So that tells me that the only way I can do this in practice is, or the only logical way is, the way I will make it 100 times faster for him is I will do the entire list. I will move one time step to the GPU, and then I will do all of these, tens or hundreds of kernels once that time step is there, and only then will I transfer another frame. But this is very different from the way VMD has traditionally done these analysis features. VMD used to do these calculations where you would, the big choice was, well, which calculation are you going to do? And since the data was already in memory, it was inconsequential to worry about having to specify up front all of the ones that you want. You just did them one at a time, and it was perfectly fine. But in the case of the GPU, because there's now a transfer cost added into this equation, it is much more logical to decide up front all of the calculations you want to do, send the data there, do the entire batch of calculations on that one data set, and then get the next data set and repeat and so on as necessary. And so that's a very different strategy. So that guides, as I revise the analysis features in VMD and the way that the commands are exposed and the way that we ask users for what things they want to do, that now tells me I have to think things over and sort of turn it inside out. Instead of saying, do this calculation on this time step, now do this other one, I may say, here's the time step I want, get that, and now do all these calculations at once. Another reason, and what's interesting is that strategy is also good if I have a trajectory that is so large that it cannot fit in memory, and the cost of reading it from disk is high, that it may take me as much time to read it from disk as to do all the calculations.
Right.
That would be a situation that is very analogous to this overhead of getting it onto the GPU. Same thing, if I'm going to read it from disk in the first place, I better know all of the things I want to do with it so that I can read it once and not several times. So it's exactly that mentality that you should think about is, if you're going to move some data to the GPU, you should use it as much as you can before you move on to the next calculation.
Yeah, and that's basically it. You want to leave data on the GPU as long as possible. So if you've got, most scientific algorithms are iterative. So you're copying data onto the GPU, you're updating some of that data. If you're running across multiple GPUs, you may have ghost cells. You only want to communicate the ghost cells off the GPU onto the other GPUs. You don't want to transfer the entire data set back and then do the ghost cell work on the CPU. Also, if you've got per cell, 10 different variables, but 8 of those are fixed and don't change during the simulation, you're only updating 2 of them, you only want to change the data elements that have actually been updated through some process on the CPU. But yeah, the ideal situation is you get the data on the GPU, you do everything you want to do as much as possible with that data on the GPU itself, and you avoid having to transfer data back to the CPU as much as possible. And it's a high-level algorithm design technique, and where it usually comes in and bites people is, if you just hear about CUDA and you look at the great flop rates, you think, okay, well, I'll transfer these two arrays to the GPU, I'll add them together, and I'll send them back. Well,
turns out that that's slower than doing it on the host.
Yeah.
Right.
Yes.
So you have to touch that data multiple times for it to work out. And that occurred to us very early on. Another thing that you should contemplate, I did a consulting job for a company here in town that does antenna simulations. And in their code, one of the cases they have, this basically does electromagnetic radiation scattering and things like this. And one of the things that happens is if you have millions and millions of little energy integrations you're doing, and depending on the parameters of the problem, some of them could be very large and some of them could be very small. For the small ones, the problem is if you do a copy of one of those bounces or integrations one at a time, there's a tremendous amount of overhead. I didn't show you guys a slide with the overhead for doing a memory copy to and from a GPU, but it takes on the order of 10 to 15 microseconds to copy 1 byte to the GPU. To copy 64,000 bytes takes only about twice as long as copying 1 byte.
10 microseconds you said for 1 byte?
Yeah, that's right. So there's a tremendous amount of startup overhead, but once you're going, you can copy bytes really fast. So like I said, if you do it right, you're going to get copies in the range of 3 to 5.7 gigabytes a second. But to achieve those bandwidths and to get that level of performance, you have to have a big enough copy operation. And so one of the things that you should consider when you're developing your own CUDA kernels is to build your data structures on the host so that when you copy them to the GPU, you can do one big copy in one operation rather than 50 little copies. Or you can batch them up. If you know that, like in the case of NAMD, as Jim described, when NAMD gets incoming messages from peer nodes, it is basically getting more work to do. Now, you could either launch those as they come in, or you can sort of aggregate it and put them in a larger and larger copy buffer and then do one big copy. And doing the one big copy is often many times faster than doing 10 or 15 or 100 little copies.
So how much did you say the 64 KB chunk would cost?
It's about twice as long as doing 1 byte.
Oh, really?
Yeah. And the other thing that's interesting is, if I remember right, if you are copying 64 kilobytes, at least on our machines, you're achieving a pretty good fraction of the peak performance. So you're maybe at 50% of peak bandwidth, or maybe not quite, maybe 40%. But it doesn't take making it bigger. I mean, so going from 64K to a megabyte. At a megabyte, you're getting basically the peak transfer performance, or so close it really doesn't matter at that point. And the reason is it has to do with how those copies are set up. So there's that setup time, there's a bunch of operating system overhead to get everything arranged just so. But once it actually begins doing the copy, it goes really fast. And so the bigger the copies are, the better your performance. So if you can put all of your data in one big contiguous buffer and just hammer it to the GPU, and the same thing coming back, you'll get much better performance on your copies.
So, and if you're either using or writing a GPU accelerated library for something, so like the FFT or loss things, there is or should be an interface that assumes the data is already on the GPU. So it's there, you just call this, it fires a kernel on the GPU. It doesn't do data transfer between steps, because the initial version of this was, okay, we're going to do FFT. You're trying to build a replacement for a CPU-based FFT, so you call this function, it transfers the data to the GPU, does the FFT, transfers it back again. Well, that was fine for dusty deck codes that you just want to be able to replace function call for function call with GPU acceleration, but in order to get sort of the best benefit out of that, and as GPUs get faster, the ratio that you need gets higher. You really want to have something where your library says, okay, either the user copies it or the library said, okay, copy this onto the GPU, make a variety of calls on that data, and then copy it back to the CPU just to support that. And I think most of the CUDA libraries that are out there now support leaving the data on the GPU.